Hello, this is Bob, and I'll be presenting on statistical machine learning principles, theory, and generalization techniques. So, to go into the main world of SML, we can see that we solve a problem that is predicting unforeseen observations using the available data. So, in SML, we define a problem, and in this context, I used a data set of a banking industry that is lending money. And the main problem was, how do you minimize risks that are attributed to loaning of people who are probably defaulters, or people who are not planning to pay back. So we formulate a problem and look at how can we minimize the risks in this context. So as we know in SML that the main target is always to predict the star, that is the bias estimator. Try to estimate what is the probability of paying and not paying. And in this context, this was a classification problem. And the assumptions made while collecting the data is that the data is always independent and identically distributed over a joint distribution of PFX, which we call it the mother. So the data qualities, we assume that it's clean, and we assume that there's no case of dimensionality where features are larger than the data. In this context, there was no sparsity. They had a number of observations with few features, but in real life, we always have such scenarios where we have a lot of features than the data set. So how do we minimize risks and balance between complexity, trade-off between bias and variance? So main context using risk minimization principle. So we have two risks, that is the expected loss over a non-distribution PFX, which is most of the times it's unattainable, and an empirical risk that is used to try to be a proxy to the true risk that is unattainable. So we use the empirical risk in the calculations to try and minimize the risk factor. And one of the main challenges we always have is overfitting, where the model tries to just remember the data instead of learning the data. So overfitting is where during training, the model performs well, but when it comes to testing with new observations, it fails. So main hypothesis step here in step 3 is try to balance complexity of the data set. We balance variance and bias, which is always, they are always against each other. One is increasing, one is decreasing. So we try to use variance bias trade-off and build an hypothesis where we're trying to build a model in case we have a model with high bias or data set that we have high bias and low variance. We use linear models, and an hypothesis where we use deep networks in case we have a low bias and high bias. How do we do optimization? So we try to optimize the performance of our data by doing regularization, stabilizing the data. So principles like Lasso and Rich try to stabilize the model by introducing penalties to false predictions. And the penalty here is the lambda times the omega of f. And for Lasso, it promotes sparsity, sets certain coefficients to 0. For Ridge, it shrinks coefficients smoothly by the omega f, that is summation of beta j squares. So hyperparameter is chosen. The lambda is lambda is chosen by cross validation. And one of the key ways where we do validation of tests is by using the ROC and the use count, where ROC, it tries to plot the sensitivity where we're looking at the true positives versus the specificity where we're looking at the probability of the false predictions across all thresholds. So let's look at the theoretical guarantee of inference, where we create a region of confidence and try to ensure that our predictions are not out of the region of confidence. So if we build an hypothesis, we ensure that we are within the dimension using, in this case, we use the VC theory, the Van Peek Chevronets. So theoretical guarantee of inference, we ensure that the confidence, the dimension of the risk factor, where we link the link between true risk and empirical risk to the model's capacity defined by the DVC, which promotes formal statistical justification how learning is possible. So how do we do interpretation of our results? We use the odds ratio, where we are looking at the expected beta rate. So significance levels, we ensure that it's a 95% level of confidence interval, and the odds ratio excludes the one. So model selection criteria using BIC and sometimes AIC for parsimony. So how do we do deployment? Deployment, transitioning our final model to production environment. So ensuring that trust of this model is close to one, and it's easy to interpret, and the model can be understandable by stakeholders and be adjusted in case there are changes in future with time. So key concepts here that just to close is generalization, then risks by looking at true risk, empirical risk, and the weight losses.